Let's finish up talking about some problems related to torque, and we will have one more topic talking about current and parallel conductors. But let's look at these problems first. Calculate the magnetic field strength needed on a 200 turn square loop 20 centimeters on the side to create a maximum torque of 300 Newton meters if the loop is carrying 25 amps. Now, the previous section I showed you the formula for this, and that is that torque is equal to N times I times AB sine theta. Now, by using the term maximum, this becomes 1, so we don't have to worry about it anymore. And here is 200. I is given at 25.0 amps. A is 0.2 times 0.2, or 0.04 meters squared. And the torque is 300 Newton meters. And so if we rearrange this to solve for the magnetic field, we get torque divided by NIB, which is going to be 300 divided by 200 times 25 times 0.04 A here, excuse me. And if we do the number here, we get 1.5 Teslas. The second problem says a 200 turn circular loop with a radius of 50 centimeters is vertical with its axis in the east-west line. The current is 100 amps. So let's write some of this down. We have the 200 turns. The A is going to be equal to pi times 0.5 squared. I is 100. And the Earth's field is the field, so that's going to be 5 times 10 to the minus 5. And it's going to be due north, and this is traveling clockwise as you view it from the west, so it's going to be doing this from the east, excuse me. So it's coming like this. So it's going to be in this direction. So if it asks for the torque, it's going to be equal to 200 times 10 times pi times 0.5 squared times 5 times 10 to the minus 5. And if you do the math here, you get 0.47 Newton meters as a maximum. And if this is this way and this is that way, then it's going to go into, if you point, actually a positive charge would cause it to go into the surface. So the fact that this is a negative direction, then it's going to come out of the page. Now here we're talking about the magnetic fields produced by a current. If you put compasses all the way around A, you'll notice that the compasses point in a circular direction, rotating counterclockwise around a current that's traveling from the bottom to the top of the page. You'll notice that there are various circles depending on how far you are from the wire. The second right-hand rule that I told you about, you put your thumb in the direction of the current and your fingers will be in the direction of the circular current or field that's going around that wire. the calculation of that field is given here in C, and it's mu sub 0 times I, which is the current, divided by 2 pi times R, where R is the distance from the wire to wherever you're measuring the magnetic field. And mu 0 is a constant that's equal to 4 pi times 10 to the minus 7 teslas. The magnet, if you're looking at two parallel conductors, you'll notice that what this diagram tends to show you is in A, if you have two parallel conductors, the fields that come out of those two are additive. And that's shown if you look at from the top. And that leads to a force that attracts the two wires to each other. So if you view it from above, which is B, the magnetic lines from each wire are such that in parallel conductors they're attractive because the currents are in the same direction, and the forces will be repulsive if the currents are in opposite direction in these two parallel conductors. Now we're going to finish up here with two examples. And here's the formula that you would use, the force per unit of length. So if you want to know the total force, you just have to decide how much of the wire length you want to look at is equal to mu sub 0 times I1 and I2 divided by 2 pi r. If they're in the same direction, they attract to each other, and if they're in opposite directions, they repel from each other. Now here's a couple of problems, and I've simplified them for example's sake here. So let's take a look at what we're going to do here. The first one, for the figure on the left, that's this figure, calculate the force on the two wires forming the base. And this is disregarding the presence of the apex wire. Now, if you want to make this problem a little more challenging, you can say, what is the force on the apex wire from each of these two wires here? And you have to use vector addition in order to do that. But let's just do this as an example. We have force per length is equal to mu 0 I1 I2 divided by 2 pi r, where r is the distance between the two. I1 is 10, I2 is 20, r is 10 centimeters or 0.1 meters, and mu 0 is 4.7 times 10 to the minus 7. I'm sorry, 4 pi times 10 to the minus, not 4.7, 4 pi times 10 to the minus 7. So if we put this in here, we have 4 pi times 10 to the minus 7 times 10 times 20 divided by 2 pi times 0.1. And these pi's cancel each other out. If you do the math here, you get 4 times 10 to the minus 4 newtons, and because they're traveling in the same direction in this situation, they attract. The second problem says if you look at this figure on the right, and it wants to know the force between this lower corner, the left upper corner and the right lower corner, disregarding these other two. And so the force on this one per length, again, is mu 0 I1 I2 times 2 pi r. So that's going to be 4 pi times 10 to the minus 7. Now I1 in this case is 10, I2 is 5. This is divided by 2 pi times, and the distance here, r, is going to be the square root of 20 squared plus 20 squared by Pythagoras' theorem. If you do that, you get 28.3 centimeters squared, or 0.283 meters. And if you do the math here, you get 3.51 times 10 to the minus 5 newtons. And now these are going in the opposite direction, and so they will repel.